I want to be able to compute areas of curved regions. For example, here's a graph of y equals x squared. Let's try to find the area of this curved region, right? The area that's above the x-axis to the left of the line x equals 4 and below the graph of y equals x squared. So this curved region inside here. Practically the only thing that I actually know the area of is rectangles. So I'm going to replace this curved region with an approximation by rectangles. The first step is to take that interval 0 to 4 and cut it up into some smaller pieces. Now I can cut the interval 0 to 4 up however I'd like. I'm just going to do it, in one particular way. I'll cut it into 3 pieces. I'll cut it into a piece from 0 to 2, a piece from 2 to 3, and a piece from 3 to 4. So I partition the interval from 0 to 4 into 3 pieces, this piece here, and this last piece here. Now I'll pick some points inside each of those subintervals, points where I'm going to end up sampling the function. These are the points where I'm going to sample the value of the function. So I'm going to choose a sample point inside each of my subintervals in my partition. In this first subinterval between 0 and 2, I'll choose a sample point at 1. In the interval between 2 and 3, I'll choose my sample point to be 2. And in the interval between 3 and 4, I'll choose my sample point to be 3.5. So I've chosen a sample point inside each of my subintervals in my partition. Now I'll build a skyscraper picture, a bunch of rectangles that approximates my curved region. So what do I mean by skyscraper picture? I just mean that I'm going to build some rectangles by evaluating my function at these sample points. So I plug in 1 into the function, and I can build a rectangle on top of my first subinterval from 0 to 2, whose height is the function evaluated at 1. On my second subinterval, I picked a sample point of 2, so I'll plug in 2 to the function and I'll get 4, and I'll build a rectangle of height 4 and width 1. Not quite to scale. And in my last subinterval, I picked a sample point of 3.5, so I'll evaluate my function at 3.5, and I get 12.25. And I'll build a rectangle of width 1 and height 12.25. Now, what's the area of those rectangles? This first rectangle has area 2 because it's got a width of 2 and its height is 1 squared. Right? I'm sampling at the point 1 and the function is the squaring function. So its height is 1, width is 2, its area then is 2. What about this next rectangle? Well, its width is 1 and its height is 4. Because the sample point here is 2, I chose to sample at 2, and 2 squared is 4, so this rectangle has area 4. This picture's not to scale at all. This last rectangle, let's see, its width is 1, its height is, well, I sampled at 3.5, so the height of this thing is 3.5 squared, and 3.5 squared is 12.25. So I've got 3 rectangles. Rectangle of area 2, rectangle of area 4, rectangle of area 12.25. Altogether, that means that 18.25, right, 2 plus 4 plus 12.25, is approximately the area under the graph. Right? I've replaced this curved region with an approximation using these 3 rectangles. So I'm approximating the area of this curved region with just the area of these 3 rectangles, which turns out to be 18.25 is my approximation. So that's an approximation, but we can do better. If I want a better approximation to the area under this curve, I'll just cut the interval between 0 and 4 up into smaller pieces. I could, in this case, consistently choose the left endpoint to sample at, and I can draw a whole bunch of rectangles now, and I could approximate the area under the curve just by calculating the area of these rectangles. And by taking more and more rectangles, thinner and thinner, I'll get an increasingly good approximation to the true area under this curve. I can also overestimate the curved region's area. I could also try to overestimate this. I could cut this interval from 0 to 4 into a bunch of small intervals and then choose the right endpoint of each of these intervals to do my sampling at, and then build this sort of skyscraper picture, again sampling at the right hand endpoint of each of my little tiny subintervals. And I can build this little skyscraper picture, and by computing the area of the rectangles, right, the areas of these rectangles are a pretty good over approximation to the area under the curve. I'm going to give a name to all these kinds of approximations. The name that we're giving to these things is a Riemann sum. Right? Riemann was a mathematician. So what's the procedure for setting up a Riemann sum? Well, it's really a multi-step process, right? Here's a picture that sort of summarizes the whole story. I'm trying to calculate the area under the curve between the points A and B, and I'm doing that approximation by approximating the curved area with these rectangles, and I can, of course, calculate the areas of these rectangles and add them up. But what's the first step? Well, the first step is to partition this interval A to B so that I can decide where to build my little skyscrapers. All right, so the first step here is to partition the interval A to B, and what that involves is choosing x naught, which is just A, and x sub n, which is B, and then choosing x1, x2, and so forth in between A and B. All right, in this picture I've chosen x1, x2, x3, x4, and I've cut it up into 1, 2, 3, 4, 5 pieces. But of course you can choose how many pieces to cut it up into. The point is just to choose how many pieces to cut it up into and then choose where you're going to make those cuts in the partition. The next step is to choose your sample points inside each of those subintervals. Yeah, after I've decided where to cut up my interval A to B, I've chosen the x sub i's, then I need to choose these blue sample points, right, the x sub I stars. So the next step is to choose sample points x sub I star, and those sample points will then be used to determine the heights of these rectangles. I'm going to be evaluating the function at those sample points. Now I can write down a formula for the area. Well, the area is approximately the areas of all these rectangles added up. Now, how big are each of these rectangles? The heights of these rectangles are coming from the function evaluated at these sample points, and the width has to do with how far apart the red cut points are. So we can write down a formula for that. Right? I want to write down a formula for the area. So the area is approximately, and this is really the Riemann sum, right? It's the sum. I goes from 1 to n, so I'm going to add up all of the rectangles, and now I got to write down the area of the ith rectangle. Well, the height of the ith rectangle is the function evaluated at the sample point, and the width of the ith rectangle is x sub I minus x sub I minus 1, right? If I take the ith cut point and subtract the previous cut point, the difference there will tell me the width of that rectangle. Let me show you on the picture again here. Right, so the height of these rectangles are coming from evaluating the function at the sample points, and the width of, say, the 1th rectangle, the first rectangle, is x sub 1 minus x sub 0. That's the width times the height. That gives me the area. And if I add up the areas of all of the green rectangles, then I get an approximation for the total area under the curve. And just to make it easy to talk about these things, there's some specific names that I want to give to particular kinds of Riemann sums. For instance, if we pick our ith sample point, so x sub I star, to be the left-hand endpoint, x sub I minus 1, then I can write down my Riemann sum like this. It's the sum over all the rectangles of f evaluated at the left-hand endpoint, that's the sample point, times the width of that particular rectangle. This is called a left Riemann sum just because I've chosen my sample points to be on the left-hand side of the interval. Similarly, right, there's a right Riemann sum where I choose my sample points to be on the right-hand side, right? So this would normally be x sub I star, but my sample point is my right-hand endpoint, so it's just x sub I. And I'm going to call this thing a right Riemann sum.